We should go ahead and get started, I suppose. It's about time. So when we last spoke, we were talking about chapter 10, which is rotational motion, and we got into doing a little dynamics, but we have a couple more dynamics type problems left that I want to solve for you. And then we're going to go into chapter 11, which actually is the way I covered chapter 10 and to some extent earlier chapters. We've gotten a good fraction of chapter 11 already done. Specifically, we already talked about the cross product as a torque, the cross product, how to calculate it, and that sort of stuff. So that's still there. But we've, like I said, already done that. So we're going to go over the remaining parts of chapter 10, and then I'm going to do some of the more pressing type problems from chapter 11. And next time, Wednesday, we'll meet and we'll discuss in a shortened way chapters 14 and 15. Uh, Pretty much you can get everything you need from the reading and from doing the online tests, the practice tests, and stuff of that sort. So remember your chapters that we're actually covering are chapters 1 through 11 and then 14 and 15. Any chapter homeworks we have outside of those are extra credit. And that's true even if they don't say EC or extra credit next to them. So just keep that in mind. Now that I've mentioned all that, I'm going to go ahead and share my screen. This is a good time, of course, for you guys to have your book open so you can look at the examples from the textbook because that's the examples I'm going to be working. So let's go ahead and share my screen with you guys. This is my iPad screen, of course. So that should pop up any second now. Okay, so you're now looking at my iPad screen. And what we have left, really, other than the stuff that we've already done, which was the last example I think we did, I actually did some examples calculating the center of mass, or excuse me, the moment of inertia. They're different examples, but I also gave you some links to examples that I've done on my YouTube channel as well. I did one that involved the parallel axis theorem, so you've seen a use of that, but you could see another example. Excuse me. You can see another example in example 1014 where they use the parallel axis theorem. I will tell you that there is a perpendicular axis theorem, but I'm not covering that and I'm not requiring you to know anything about that. So you do need to expect to be able to use the parallel axis theorem, but not the perpendicular axis theorem. And of course, you need to be able to do the integrals required to calculate the center of mass, or excuse me, the center of mass too. That was from chapter 9, but also the moment of inertia. Remember, the center of mass is the integral of x dm divided by the integral of dm. Y would be similarly, y center of mass would be similarly calculated, and the z center of mass would be calculated similarly as well. But the moment of inertia is the integral of r squared dm, where r is the perpendicular distance from the axis of rotation to the differential mass element dm. So those are things you do need to be able to do. So make sure you look at examples 1018, or excuse me, 1014 and 1013, even though, like I said, I've done something like them, and 1013 I've actually done in on my YouTube channel and posted those as well, so you can check out as much of that as you want. But if I move on to page 281, we introduce a new version of kinetic energy. So we have kinetic energy, obviously, but we also have a kinetic energy. What am I looking at over here? That's weird. Okay. I've got two screens open for some reason showing your name, so I was just trying to figure out why. And now I'm going to try to get the chat window open. There it is. Okay, now I've got the chat open so I can see that. But there's another kinetic energy. So we've learned kinetic energy is 1/2 mv squared, but that's the kinetic energy of something just moving along in any direction. So you can have a 1/2 mv squared for an object moving this way, in which case you might call it 1/2 mvx squared. But you also might say it's moving this way, then you have a 1/2 mvy squared, and then you might say it's moving this way, then you have a 1/2 mvz squared. And of course, vx squared plus vy squared plus z squared square root is v. So you could just replace all that with 1/2 mv squared. But what if, in addition to this translational motion, which might do something like this, what if the object's rotating? Well, if it's rotating, it has an additional kinetic energy, and that kinetic energy is called rotational kinetic energy. So what we'll say is K rotational is equal to 1 half I omega squared. Notice how that fits exactly in our analog that I've been telling you about the kinematics and dynamics of rotational motion versus linear motion. Specifically, the kinetic energy for linear motion was 1 half mv squared, and the rotational analog to mass is the moment of inertia I, and the rotational analog to velocity is the angular velocity or angular frequency omega. So this completely fits with that. Now, the key point is that this 1 half I omega squared, your book points out that it's rotation about a fixed axis. If the axis is not fixed in space, rotational kinetic energy can take on a more complicated form. And we'll show you roughly what we mean by that. So let's go ahead now and work on example 1015. So this is from your text again, example 10-15. So this one says flywheel, and it's an estimate problem, so you're supposed to be estimating. It says flywheels, which are simply large rotating discs, have been suggested as a means of. I'm sorry, I stayed up late last night by mistake. Well, not by mistake, I just couldn't sleep, and now I just can't stop yawning. So, anyways, flywheel. Flywheels are simply large rotating discs, and they have been suggested as a means of storing energy for solar-powered generating systems. Estimate the kinetic energy that can be stored in an 80,000 kilogram, that's 80 ton, flywheel with a diameter of 10 meters, like the size of a three-story building, assuming it could hold together without flying apart due to internal stresses at a rotation rate of 100 RPMs. So what we have here is M is equal to 80,000 kilograms, which you could also write as 8 times 10 to the fourth kilograms. Since we're doing estimating, they're only expecting more or less one sig fig anyways. We have a diameter, D, which is equal to 10 meters, and we have an angular frequency, omega, is equal to 100 RPMs. And what we want to calculate again is estimate the total kinetic energy or the rotational kinetic energy. So K rotational is equal to question mark. So in this case, what we're going to do is we're just going to say K rotational is equal to 1 half I omega squared, and they said it was a large rotating disk, and we know the moment of inertia for a rotating disk, because I derived it for you last time, is 1 half mr squared. So I can write this as 1 half times 1 half m r squared, which we have d, not r yet, but we can deal with that, and then times omega squared. So in order to do this, I want to write down the 1 half, and then another 1 half, and then 8.0 times 10 to the fourth kilograms. Now, R is half of the diameter, so I'm just going to write this as 5 meters squared. And then I've got to convert the 100 RPMs to radians per second, or the units don't work out. So I'll say 100 RPMs means revolutions per minute. Now I have to take one revolution and realize that that is equal to 2 pi radians. So that will get rid of our revolutions and turn it into radians. But now I also have to take our minutes and turn it into seconds. So I'm now going to say that 1 minute is equal to 60 seconds. Now, of course, that omega still has to be squared, so we still got to do all that stuff. And now we can go ahead and calculate it. I'm going to say 0.5 times zero point 0.5 times 8 times 10 to the fourth times 5 times 5. Notice the 5 had to be squared because it's r squared. And then times, let's do parentheses, 100 times 2 times 3.14159 times, or actually divided by 60. And now I'm going to, yeah, 1 minute, 60 seconds. Yeah, that's good. Now I'm going to put an end to those parentheses and square that. And this gives me 5.4 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the seventh. And that unit should come out in joules. So 5.4, actually, I should round that to 5.5 because it's 5.483. So the energy stored there is on the order of 5.5 times 10 to the seventh joules. That's how much energy it has at any one time. If you want to consider what that is in kilowatt hours, we know that 1 kilowatt hour is equal to 1,000 watts. In other words, a kilowatt is 1,000 watts, and a watt is a joule per second. And then times 1 hour, and 1 hour, of course, is 3,600 seconds. So I write 3,600 seconds over 1 hour like this. And that gives us roughly 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. So K rotational is equal to 5.5 times 10 to the seventh joules. Doing a unit conversion, so I write that over 1, just as we learned early on. And what we know is that 1 kilowatt hour, which is what we're wanting to convert this to, is equal to 3.6 times 10 to the 6 joules. So if I divide this number by 3.6 times 10 to the 6, I get about 15 kilowatt hours. So just to give you an idea, if you were, let's say, running something that only took 3 kilowatts, then you've got 15 kilowatt hours. So we'd only get 5 hours out of it. So that gives you an idea that this disk is not necessarily that helpful, even though we used one that was 80,000 kilograms and spun it at 100 RPMs. That's still pretty fast. So the flywheel is not a really good application, at least not for solar power. However, they have thought about that for satellites, space stations, stuff of that sort. So it might still be fairly useful in those cases. Anybody have any questions on that? All right, let's try another example. This is example 10-16. And it says rotating rod. A rod of mass M is pivoted on a frictionless hinge at one end, as shown in figure 1030. The rod is held at rest horizontally and then released. Determine the angular velocity of the rod when it reaches the vertical position and the speed of the rod's tip at this moment. So what I'm going to do is go ahead and draw the diagram so you'll have some idea what we're talking about here. But you can imagine that we're going to have an axle, if you will, and that's what that circular green dot is right there. And now we're going to imagine that affixed to that is more or less like a hinge. Okay. So we have this rod right here, and its length is L. Now, technically, that should go right about to the center of the rotation of the circle. That's sort of what I'm trying to do here. I made that hinge and axle a little bit bigger compared to the dimensions of the rod than it really should be, but it's okay. I'm just trying to give you a rough estimate. Now, the center of mass, of course, is at L over 2, which I might say right about, it should be right about here roughly. So that's really where the center of mass of this system is, or specifically the center of mass of this rod is right there. And that's going to come in handy because we're going to use conservation of energy. And one of the ways you can deal with conservation of energy is you can talk about the not only the kinetic energy, but you can talk about the potential energy, and you can reference the potential energy as m times g times the height, say, of the center of mass. It really doesn't matter that you go to the center of mass, but as long as you have a physical spot that you can point at both at the beginning and end and is easily discernible, then that's fine. So that's why I'm using the center of mass. Now, what's going to happen is this whole thing is going to rotate down 90 degrees like this. Okay, and what we're trying to figure out is determine the angular velocity of the rod when it reaches the vertical position, and they want to know the speed at the end. So what I want to know right here is uh, is what is omega, and also what is v tangential. Okay. So we can use our conservation of energy. And remember, the conservation of energy, the way I showed you guys, was K initial plus U initial plus work in is equal to K final plus potential energy final plus E loss plus work out. Okay. In this case, we're not really compressing any springs. We're not adding any forces or anything like that. So the work and the E losses are all essentially zero. So we're going to say approximately zero, approximately zero, approximately zero. The kinetic energy, since we're dropping it from rest, is going to be equal to zero initially. And the potential energy, on the other hand, is going to be the mass of the object, which I didn't write it on here, but the mass is big M. So it's going to be M times G. Now, the height would be, if we consider right here, this center of mass is going to fall down to here. So we can, in principle, call this height u equals 0, in which case, right now, the height is L over 2, which is basically the height of the center of mass. So I'm going to say mgl, oops, should probably stick to the green. Mg times L over 2 is the potential energy. And then when it reaches the bottom position, the potential energy is 0, but the kinetic energy is just rotational motion. So it's going to be 1 half I omega squared. And in this case, we have a rod rotating about its end, and that happened to be one of the derivations I did. But in case you forgot, you can also use I is equal to 1/3 ml squared. So I'm going to say I is equal to 1/3 ml squared, and I'll write end on that because that's what it is. Ooh, I wrote 1 half even though I said 1/3. I'll write end on this because this is the moment of inertia about the end. Okay, so now I'm ready to fill in the conservation of energy. What I'm going to have is m times g times L over 2 is equal to 1 half I. Now I is going to be 1/3 ml squared times omega squared. And omega is one of the things we're wanting, but you can immediately see that the m is going to cancel out with the m on the other side. You can also see that the 2 over here is going to cancel out with the 2 over here, and that the single L on the left is going to cancel out and leave a single L on the right. So now I have G is equal to 1/3 L omega squared. So omega, which is what we were asked to find, is going to be square root 3G over L, like that. And maybe I didn't make that L big enough for you to understand that it's an L, not an E, so I'm going to try to soup it up a little better. So that is the angular speed that it has as it reaches the bottom. Square root 3G over L. Anybody have any questions on that? Now we also use V equals R omega to find that V tangential is equal to L times omega, and omega is the square root of 3G over L. I can pull the L inside by squaring it, then it becomes the square root 3G L squared over L. And of course, that tells us that V tangent, that tells us that, well, darn it, that tells us that V tangent is equal to the square root of 3. Ooh, actually, I don't need a fraction now. It's just 3 times G times L. Now, if you actually dropped an object and it fell a distance L over 2, then basically you would have a new speed given by V equals, well, we could use conservation of energy again. And what I could say is like this. Let's say we're just dropping in an object. It'd be M times G times L over 2 is equal to 1 half M V squared. Those two M should have been the same. I drew one lowercase and one uppercase. That's stupid. V squared like that. Now we can see the M's cancel out, and what you get is V is equal to the square root of G times L. And that's mainly because we used L over 2 as opposed to L. If we'd used L, it would have been 2 times G times L. But the main thing you can see is clearly the velocity at of the tip is quite a bit faster than the velocity of an object that would have fallen straight down. That's partly because the effect that we talked to you about when I was talking about pulling a water skier, for instance, behind a boat, when they swing out wide, then the boat's making a radius, a turn of a certain radius, but the skier is extended an even larger radius, and that larger radius, given that v is proportional to the radius and the omega for the boat and the omega for the skier are supposed to be the same, that means clearly the velocity for the skier is going to be markedly faster. And that's what's going on here. We're talking about the velocity of the very end of the rod. So, anybody have any questions on that? I'm going to circle the wrong one. All right, so that's just some quick and dirty and quote unquote easy calculations with this new kinetic energy formula we have. Now, in general, when an object, for instance, rolls down an incline, it has kinetic energy associated with the center of mass going down the incline or whatever, plus the moment, or excuse me, the kinetic energy associated with it rotating. So the total kinetic energy becomes 1 half mv squared plus 1 half I omega squared. And we can also combine with that the idea of rolling without slipping. And then from S equals R times theta, you get V equals R times omega and A equals R times alpha. Those are the three types of equations you can use if there's rolling without slipping. So that'll come in handy as well. Anybody have any questions before I move on to the next example? Your book also talks a little bit about the instantaneous axis, And that's a very nice thing to do. And in fact, you can use that as the quote unquote pivot point, if you will, when you go to calculate torques and stuff of that sort, is you can use that very bottom. The neat thing is, as the wheel, for instance, rolls down, as that spot on the wheel gets to the very bottom, at that instant, and only at that instant, that particular spot has zero relative velocity to the road. But then immediately it moves with respect to the road shortly thereafter, and of course it was moving with respect to the road shortly before that. So, anyways, just keep that in mind, and we're going to work a problem example 1017. So let's go example 10-17. Now, this one says sphere rolling down an incline. What will be the speed of the center of mass of a uniform solid sphere of mass big M and radius r0 when it reaches the bottom of an incline if it starts from rest at a vertical height h and rolls down without slipping? So let me draw the figure first and then I'll do some labeling. So what I'm going to say is this height right here is h, and this angle right here is theta, so that might come in handy. And what we have is we can imagine a sphere that's sitting right at the top, and of course, the radius of that sphere is r0, and the mass is big M. So those are the variables we have, and what we want to know is what will be the speed of the center of mass of the sphere at the bottom. So when the sphere gets to the bottom, the center of mass is question mark. That's what we really want to do. No. Okay. So I'm going to use my conservation of energy, and that is K initial plus U initial plus work in is equal to K final plus U final plus E loss plus work out. Again, we're not doing any of those special things. So workout is going to be zero, E loss is going to be zero, work in is going to be zero. We said it started from rest. I should indicate that by saying V0 equals zero and omega zero is equal to zero. Now, with that in mind, we can also say that the kinetic energy must be equal to zero initially. And then at the bottom, the potential energy is going to be zero. So I can put a zero there as well. Now that I have all that, I can say specifically if we treat this zero of height as u equals zero, then our conservation of energy equation is going to become m times g times h plus r0. Notice the height is to the bottom of the ball, and then the center of mass, which we're choosing to use, you don't have to. You could actually measure it from the bottom if you wanted to, but the height to the center of mass is an additional r0 upward from the bottom. The At the bottom, we're going to have a kinetic energy associated with the center of mass rolling down. So we're going to have 1/2 mv center of mass squared, but it's also going to be rotating without slipping. So we have a 1/2 I omega squared as well. Now the I for a sphere, now this one you can in principle work it with a single integral, but it's quite a mess, and you might not want to. But if you could allow yourself a double or triple integral, it can be very straightforward. So that's why I didn't derive that for you, and I'm not going to require you to be able to do that for us. But the result is 2/5 m r0 squared. So I can now put all this stuff in, and I have mgh plus mgr0 is equal to 1 half m v center of mass squared plus 1 half times 2/5 m r0 squared times omega squared. Now we have, since it's rolling without slipping, we can use V is equal to R omega. And that V is, of course, the center of mass velocity we've been talking about over here. So that's going to come in handy. And I made it so small I can't even subscript it. But V center of mass is equal to R times omega. And that means since they asked specifically for the V center of mass, they didn't ask for the angular speed at the bottom, then I'm going to choose to eliminate the angular speed. So omega is going to be equal to V center of mass over R. Now you can also see before I do that that the M is going to be present in every term, and therefore we can divide through by it and it will disappear. So now I have GH plus GR0 is equal to 1 half V center of mass squared plus 1 half times 2/5 is 1/5 R0 squared, and then omega is equal to V center of mass over R0, and of course that's got to be squared. You can see immediately that because of that square, the R0 here is going to cancel out with the R0 squared up here, and we can now say that oops. Did anybody catch that the moment or the potential energy at the bottom is not exactly zero because I ended up using the additional height R0? In other words, I measured the height up to the center of mass. The object actually has some potential energy at the bottom. So let me fix that real quick. I don't know why I just thought of it all of a sudden, but it's not that. The only difference is I'm going to say, and I'll write it here in red just to make sure you see that I'm adding it. This one's going to be M times G times R0. So over here it's going to become plus M times G times R0. And the main reason I wanted you to see that is because the GR0, when I divide through by the M, the GR0 is still going to exist on this other side. So now I can say subtract GR0 from both sides, and we'll get right back to where we were. Okay, so sorry I left off that potential energy. Hopefully someone caught it. Hopefully y'all noticed it and just didn't say anything to me. But if you didn't, try to watch a little closer. That being said, we've got G times H on the left-hand side. And then on the right-hand side, we've got 1 half V center of mass squared plus 1/5 V center of mass squared. The least common denominator between 2 and 5 is, of course, 10. So if I multiply the 1/5 by 2 over 2 and the 1 half by 5 over 5, I'm going to get 7/10 times V center of mass squared like that. And then lo and behold, that means the velocity of the center of mass is going to be equal to the square root of 10 over 7 times GH, which remember before we had 2GH for something that falls a different falls a distance h. The velocity at the bottom, if it started from rest, was the square root of 2GH. In this case, we got 10/7, which is a little smaller than 2. Uh, it would have to be 14/7 for it to be 2. So 10/7 is clearly smaller than 2. And that should make some sense because not only are we allowing the potential energy to be converted to kinetic energy, we're allowing it to be converted to linear kinetic energy plus the kinetic energy associated with rotation. So obviously we got to steal some of the potential energy just to make the thing rotate. All right, specifically the sphere rotate. So that's what the velocity of the center of mass of the ball will be at the very bottom. Anybody have any questions on that? All right, so I think that's a pretty straightforward, nice, useful example and way of showing you how we can use conservation of energy to solve a physics problem. Another problem they do in this one is a conceptual example, and it's called example 1018 conceptual example, which is fastest. It says several objects roll without slipping down an incline of vertical height h, all starting from rest at the same moment. The objects are a thin hoop or a plain wedding band, a spherical marble, a solid cylinder like a D cell battery, and an empty soup can. In addition, a greased box slides down without friction. In what order do they reach the bottom of the incline? All the objects have the same mass m and radius r if rolling. Okay, so this is a conceptual example, and it's conceptual example 1018. I'm going to draw a picture of it just to give you an idea what we're talking about. So we're basically allowing an object, and it's actually several different objects, where imagine this is a very wide ramp where we can put all these things side by side by side. And if we did that, then you can sort of think of it like this, something like that. And then, of course, oops, let me make it a little lower down. I'm going to use my lasso to move it. Say copy. Let's say cut, actually. I'll say paste. Okay, so now that's the object. And what we're going to imagine is a thin hoop, which they said was like a wedding band. So I can just draw a thin hoop right there. So that'd be hoop. And then we're going to draw a spherical marble. So that'll look exactly the same. And then we're going to have a solid cylinder. Now that one will definitely look a little different. And we're also going to have a empty soup can. So that's a hollow cylinder. And then, of course, we're also just going to have a box sliding down, which I'm not even going to bother drawing, but sliding without friction is the main thing. So, using our conservation of energy, we can say that all of them, with the exception of the box that's greased, so M, the potential energy for all of them, U initial, is given by U initial for the hoop is equal to M times G times H. U initial for the sphere is M times G times H plus R0. Or let's say H plus big R. R0 is what we used before, but I want to use big R. And I think that's what they even told us. Yeah, they said big M and big R. Then we have U initial for the solid cylinder, so I'm going to call that SC. That's going to be MGH plus R. And we also have the hollow cylinder, so I'm going to say U initial HC is equal to MGH plus R. And then that's it. We actually have all the different shapes there. Uh, Notice the actual. Did I even put that one there? Oh no, I didn't put the just the little blocks that's greased. So I'll say U initial, and they called it what? A greased box. So I'll call this GB. Its potential energy is just M times G times H. Okay, but notice the final potential energy will be M times G times 0 for the GB, where it's going to be M times G times R for all the other things. So now I can say U final. In this case, I'm going to say U final for the hoop is equal to mgr. U final for the sphere is equal to mgr. U final for the solid cylinder is going to be mgr. And U final for the hollow cylinder is going to be mgr. And U final for the grease box is just going to be 0. Okay. So now what we can do is we see that U accidentally went into automatically drawing uh, a preferred shape. So I'm going to say U initial is equal to K final. In other words, I've taken the time to mark out all the E losses and work in and work out and kinetic energy that's 0, all those little things that are initially 0. I've went ahead and canceled all those out. And now all I have left is U initial is equal to K final plus U final, which in one case the grease box is going to be 0, but in other cases not so much. So what I can do is I can say mg h plus r, that's the left hand side for all of them, is equal to 1 half m v center of mass squared plus 1 half. Now, the trick with the moment of inertia is the moment of inertia formula is always some number times mr squared. So I'm just going to put n times mr squared. That's my moment of inertia. And then that's times omega squared. And then I want to say plus mgr. And this is for everything but the greased box. Okay. Now you can immediately see that the mg, or excuse me, the m is going to cancel out from each part. We can see that the GR is going to cancel out with the GR over here. And what we're going to have is H equals 1 half V center of mass squared plus 1 half N r squared. Now, omega, since we're assuming it's rolling without slipping, omega is going to become V center of mass over r, and that's all going to be squared. And from that, you can see that the r's are going to cancel out, and what we're going to have is basically a common factor of 1 half and VCM squared. But in addition to that, we're going to have 1 plus n, where n is whatever that number is in your moment of inertia. So now that we have that, we can say that the V center of mass is going to be equal to I think I dropped off my G, and that G should have stayed there. Let me fix that real quick. Yeah, I said the G. Oh, I know why. I canceled out the G with the R so I could do it on both sides, but the G with the H was still there, so this still has to have a GH there. Sorry about that. But now I can go ahead and solve this, and what I'm going to get is a square root of 2. Oops, I was writing in red. The square root of 2GH over 1 plus n. So you can see that basically the velocity that the object will have at the bottom is going to be inversely related to the number that goes in front of the moment of inertia. So for a hoop, I is equal to mr squared, which implies n is equal to 1. For a sphere, I is equal to 2/5 mr squared, so n is equal to 2/5 or about zero point 0.4. For a solid cylinder, I is going to be equal to 1/2 mr squared, which means n is going to be 1/2 or zero point 0.5. And then for a hollow cylinder, it's essentially going to be the same thing. If it had an end cap, like a top and a bottom, you'd have to make a little bit more adjustment. But usually speaking, the mass of the end cap is probably fairly small compared to the mass of the sides of the can. So I'm going to say the hollow cylinder actually has well, I don't know. I'm trying to remember, would the hollow cylinder? Well, let me look at what your book did. I don't know if your book actually took into account the fact that the hollow cylinder might have had a top and a bottom. The empty can, which is also a hoop plus a thin disc, has most mass concentrated at R. Okay, so yeah, it's saying the factor might be a little bit less than 1, but because some of it's actually distributed at a radius less than R. If it was all at R, it'd just be mr squared. So we're going to say like 0.99. So hollow cylinder I is about 0.99 mr squared. So that means n is approximately 0.99. And that's the four objects that we have there. So what we can see is that the ones with the largest n value are going to have the slowest velocity or the lowest velocity, and therefore they're going to end up getting to the bottom at the last, because this is true for every instant in time. As soon as they leave, the velocity is going to sort itself out such that the one with the largest n value will be going the slowest, and the next largest would be next slowest, and the next largest would be next slowest, and so on and so forth. So what we can see is that the hoop would be dead last. Then we'd have the hollow cylinder, and then we'd have the solid cylinder, and then we'd have the sphere. But the neat part is the greased block is actually going to be faster than all of them, because all of its potential energy, mgh, is going into 1/2 mv squared. So we're going to get basically v is equal to the square root of 2gh. So the answers turn out to be fastest, which I'll say first, to slowest, which I'll say last, is going to be the very fastest is in fact going to be the greased block. And that's because it's going to be the square root of 2gh. And you can see 1 plus n is never going to be as big as 2, since it's 2 divided by 1 plus n. 2 divided by 1 plus n is never going to be as big as 2 unless n is truly 0, and we don't have that. Okay, so the grease block is going to be the fastest, And then the second fastest would be the solid cylinder. And then the third fastest will be, I'm supposed to be going smallest to largest. So the greased one, and then one half was small. Oh, nope, should have been the hollow, or should have been the sphere first. Sorry about that. Because point 0.4 is less than that. So sphere is next. The grease block, of course, being much smaller. So the sphere is the lowest in, and then the second lowest in is the solid cylinder, and then the second slowest is the hollow cylinder. Oops. And then after the hollow cylinder, which is like the 0.99, we have the hoop. So the hoop would be dead last. And that's the answer. Anybody have any questions on that? So hopefully the way I did that was fairly explanatory. If not, look back at the way the book did it. Maybe you'll like that one better. Maybe solve it yourself. See which way you like the best. The main thing is we're going to go ahead and move on and attempt to do example 10, 19 now. And no questions on that, anyone? All right, let's go to example 10, 19. So example 1019 says analysis of a sphere on an incline using forces. So analysis of a sphere on an incline using forces says analyze the rolling sphere of example 1017, figure 1034, in terms of forces and torques and determine the velocity v center of mass of the sphere's center of mass at the base of the incline and the magnitude of the friction force F sub FR. Okay. So what they want to do, I'm going to go ahead and draw a figure for starters. Let's say this height right here is H. And let's say it's going to go down an incline. And this angle right here is, say, theta. And what we're going to have is a ball, a sphere, if you will. Okay. Acting on this sphere is a normal force, which I'm just going to call N. And then in addition to that is a weight, mg. And in addition to that is a friction force, which your book is calling F sub F. Actually, they said F sub FR. I think I'm going to just do F sub F because that's enough letters to write on there. Okay. Now, in order for us to do this, as I've warned you guys, when you're doing any kind of inclined plane other than a banked curve, it's almost always best to go ahead and tilt your coordinate system. So that's what I'm going to do. I'm going to imagine, for instance, that our coordinate system is the positive x-axis pointing straight down the incline and the positive y-axis being perpendicular to the incline. And that means that I can break this mg force up into this one. Now, notice since the angle that I drew on the incline is theta, this angle right here is 90 minus theta. But the angle between this purple part right here and this is also 90. So that means this angle up there has to be 90. And therefore, we get mg sine theta and mg cosine theta. the mg sine theta being that bottom one, and the mg cosine theta being the one that's pointing down and to the left instead of down and to the right. Now, all we have to do is actually, we were asked specifically to find what was it? Analyze the rolling sphere in terms of forces and torques, determine the velocity. So we want the VCM equals question mark, and we want the force of friction equal to question mark. So first off, what I'm going to do is I'm going to take the summation of forces in the y direction is equal to 0. So the summation forces in the y direction equals mass times acceleration in the y direction. But we're not expecting the sphere to be bouncing up and down on the incline. It's just going to have a constant y value. Therefore, the acceleration in the y direction is going to be 0. But in the y direction, that's going to give us n minus mg cosine theta. That's all the forces acting in the y direction, so that equals 0. And what that tells us is that the normal force is actually equal to mg cosine theta, which we sort of knew already. So I'm going to take that as equation 1. Now I'm going to do the summation forces in the x direction equals mass times acceleration in the x direction, only this time I can't be so bold as to assume the acceleration in the x direction is 0. In fact, we have to sort of figure out what it is to some extent. So I'm just going to leave it as a, and since it's the only one, I'm just going to leave it as a with no subscript. But in this case, the only forces I have acting are the mg sine theta, which is in the positive direction. So I'll say mg sine theta minus the friction force, which is F sub friction. And that's all equal to the mass times the acceleration in the y direction. And that's really the acceleration of the center of mass. So we could, for instance, label that as a center of mass, but I'm just choosing not to use any subscripts because I don't want to. Now that I have that, I can go ahead and realize that in this case, we can treat the rotation axis as a fixed axis through the center of mass. So it's actually fixed in direction. So the center of mass, or excuse me, the axis of rotation is perpendicular to the page and goes right through the center of that sphere, which is the center of mass. That means the summation of the torques about the center of mass is equal to I times alpha is acceptable. So now I can say the summation of the torques about the center of mass is equal to I times alpha about the center of mass. And I'm going to be ditching that center of mass there as well, just like I didn't put it on the A. But what we see is the mg is the weight, and by definition, gravity pulls on this sphere through its center of mass. So the lever arm for the weight is 0. Similarly, you can see that the normal force goes right through the center of mass as well. So the torque due to that one's also 0 because there's no lever arm. So in fact, we only have one force tending to cause a torque, and that's the friction force. And that force happens to be perpendicular to the lever arm. So the torque is just F friction times the radius of the sphere. And the radius of the sphere is, they didn't actually show it, but if we looked back at the original example, 1017, I think it was R. Yeah, it was R0. That's what it was. Sorry about that. So what we have is F friction times R0 is equal to I. Now remember, I for a sphere is actually 2/5 mr squared. So I'm going to say 2/5 m. Oops, we're using lowercase m. So 2/5 m R0 squared times alpha. So this will be equation 3. And we're also assuming that it rolls without slipping. I was trying to make sure it said that, but that was part of the original example, was that it was rolling without slipping. It says sphere rolling down an incline. What was the speed of the center of mass of a uniform solid sphere of mass m, radius r0, when it reaches the bottom? uh, and rolls without slipping. So we're referring to that previous example, which was 1017, and in 1017 they said it was rolling without slipping. So we're going to assume the same thing. So rolling without slipping says says that the V center of mass is equal to R0 times omega, and that's going to be equation 4. Now that we have all this, we can go about trying to solve for various things, like what they asked for was the center of mass velocity and the friction force. Right now, I feel like I can solve for the friction force pretty straightforward by, that equation 4 was V center of mass, but we could also get equation 5, which would say A center of mass, which is all we're calling just plain A, is equal to R0 times alpha. So both of those are acceptable, but probably 5 is the one we're going to be using. Now, with that in mind, what I'm going to do is go ahead and plug in the rolling without slipping equation 5 into 3. So plug 5 into 3. And with that, I get F friction R0 is equal to 2/5 M R0 squared. Now, alpha is going to be A over R0. So you can see that the R0 in the bottom is going to cancel out with one of the R0s up here, but then the other R0 is going to cancel out completely. So what we get is that the friction force is actually equal to 2/5 times M times A, but we don't know A yet, so we didn't really solve anything yet. But that is something that we can plug into. I'm going to call this equation, let's say 3 prime. Actually, I should really call it 6. It's a whole new equation. So I'm going to take equation 6, which came from 5 and 3, by the way. I'm going to take equation 6 and I'm going to plug it into equation 2. So plug 6 into 2. And when I do that, I get mg sine theta minus 2/5 ma is equal to ma. So you can see already that the m's cancel out. And we can pull the 2/5 to the right hand side, and that'd be 2/5 plus 5/5, which would be 7/5. So I'm going to get g sine theta is equal to 7/5 a, and specifically that'll give us that a is just equal to 5/7 times g sine theta, and that is, though they didn't ask for that, that is an acceleration that we can make use of. Okay. It is a constant, so we know our kinematic equations work. So now I can use that to figure out what the velocity of the center of mass is. So what we can do is say V equals V0, or actually, since we know the distance, we want to use the V squared equation. So I'm going to say V squared is equal to V0 squared plus 2A x minus x0. From the diagram, we're going to say x0 is, of course, we can always make this the case. We're going to say x0 is 0, but from the diagram, we can see that x can be given by considering the sine of theta. Sine of theta equals opposite over hypotenuse. The opposite is h, and the hypotenuse is x, the distance traveled as it rides down that incline. Therefore, x is equal to h over sine theta. Now I can plug all that in and find that v squared is equal to v0 squared. And by the way, v0 was 0. So it's going to be equal to 2 times a. And a we found was 5/7 g sine theta. And then times x, which we found was h over sine theta. So what we can figure out from all this is that clearly the sine thetas cancel out, and I'm going to get basically v is equal to the square root of 10/7 g times h. I don't know why I wrote half of that in red, half of that in blue, but we did. So v, which equals v center of mass, is going to be the square root of 10/7 times g times h, which, by the way, is exactly what we got when we did it with conservation of energy methods in example 1017. Let's see. Yeah, there it is. So remember, we got square root of 10/7 times GH, but notice how much easier the conservation of energy method was compared to the Newton's second law version. Now that we have all this and we know what this A is, we can now find out what the friction force is. So the friction force, F friction, I don't like my writing today. It's not making me happy at all. So F friction we found was in fact 2/5 M times A. I don't know why I wrote a G there, but M times A. And that's 2/5 times M. But A we found was 5/7 times G sine theta. You can see that the 5 in the denominator cancels out with the 5 in the numerator, and therefore we get that the friction force, F friction, is actually equal to 2/7 times mg. This is really bad writing day for me. It's 2/7 mg sine theta, and that's our friction force. Now, if we wanted to, we could go ahead and set that equal to mu normal times or excuse me, the mu static times the normal force, and that could give us a coefficient of friction if we wanted to, and so on. But that's plenty enough for right now. Does anybody have any questions on that? All right, your book does two really much more cool examples in example 1020 and 1021. I would really like you to take time to look at that, but that's a little harder than I plan on testing you. Not because I think that's too hard for this course or it's too hard for my students, just because I'm having to do this chapter 11 and chapter 10 in a little shorter time frame than I'd like to. So I'm just going to skip those two examples and just let you know that, hey, we're not going to do something that brutal on the online test, which remember I did open up a sort of extra credit last online test that goes through these chapters. But it's extra credit in the sense that now I'm not dropping the single lowest online test, I'm dropping the two lowest online tests. So, in some sense, it's like it's just an extra credit test. I highly recommend you take it, though. Now, with that being said, we have essentially finished chapter 10. There's really not much more for me to do. The 1022 is actually a really good example, and that explains something like if you've ever noticed, if you take off in a car, especially like a rear wheel drive car, front wheel drive is a little bit different to analyze, but with a rear wheel drive car, you will notice that when you hit the accelerator, the back end sort of goes down of the car, and you might wonder why is that the case. Well, that's what example 1022 does. So I definitely recommend you check that out, even though, again, that's a little bit more advanced problem. But 1022, 1021, and 1020 are quite a bit more complicated than I'm going to require of you guys. So does anybody have any questions on that? All right, we're going to go ahead and move on to chapter 11, but I think this might be a good time. Let's let you guys go ahead and take a break. It's 6:39. Come back at 6:45. I'm here if you need me. If you have any questions, I'll still be here. But let's go ahead and give you guys a 6-minute break. So, see you at 6:45. Question about the face-to-face test. Is it possible for you to make it so that we can see our results? Uh, Gabe, yes, that's supposed to be visible to you for all those tests. Specifically, what you have to do though is you have to open up your lockdown browser and then go, or at least what I've traditionally done is go to the grade book and then click on your grade for face-to-face test one or face-to-face test two or face-to-face test three, and then you can actually see it. It won't give you the correct answers, but it will show you which ones are wrong and it'll show you all the answers. So that's what's supposed to happen. If it's not working that way, though, let me know. Speaking of which, I just remembered a student told me that they were having difficulties in that they could not uh, take the self-proctored final. So let me double check that real quick while we're waiting for everybody. So I'm going to the self-proctored face-to-face test. It said she said it was asking for a password, and darn if it's not asking for a password. I don't know why I did not do that, but let's see. Let's see if this works now. And it doesn't have any lockdown browser, but it does require a respond to this lockdown browser. Maybe that was the reason that it automatically did that. Let's check in lockdown browser, make sure it's not acting funky. Okay, lockdown browser, face to face test 3, face to face test 3. She had the word self on it. Looking for it, looking for it. That's not it. That's not it. Self. Look for the word self. For self-proctoring. There you go. Ah, yep, that's exactly why I had it in the settings for the lockdown browser. Okay, that should be taken care of. Now I'm going to open up the other course, the O01B, and make sure they don't have the same problem there. We got about a minute left for those of you taking your break right now. Okay, I got rid of it there. Let's check in the lockdown browser now for self-proctoring. All right, it's time now, but I'm going to go ahead and finish this real quick before or else I forget it. There it is. Settings, advanced settings, save and close. Okay, that should work now. All right, so it's time to go ahead and get started. I've answered Gabe's question, and Gabe was good enough to remind me of another student's question, so I've taken care of that. Thank goodness that happened. I wrote myself a note, but then I got sidetracked and probably would have forgotten it until I got a call saying I can't take the test. So I wrote something at the top of the page. It says examples 10, 20, 10, 21, and 1022 are great and reasonable for the course, but I have skipped them to let you know you will not be tested at that level. It's perfectly reasonable for your homework to be at that level. It's perfectly reasonable for your even for your practice tests, even though I tried to cut those out. It's perfectly reasonable for them to pop up there, but I am not going to test you at that level on the last test nor on the face-to-face final. So just keep that in mind. We are jumping into chapter 11 now, and chapter 11 is on angular momentum. As I mentioned earlier, uh, this is a chapter that I've already done a lot of work in, and therefore it won't have to go quite as long as you might think. But it starts off with a really nice example. So you can imagine a person, and if you look at the opening page for chapter 11, you'll see, for starters, an ice skater in the air, jumping, her skirts out, like a level plane. In fact, her skirts shot out that way, and her arms are tucked in like this, and she's clearly in a rotation, and she's also off the ground. It appears to be a little bit off the, I shouldn't say ground, above the ice skating rink floor. Okay, but that's a typical example of angular momentum. So, for instance, if you were to watch her and she starts to spin when her arms are completely out like that, that allows her to have a large moment of inertia. Because remember, the moment of inertia is the mass of each individual particle in her body, say, times the square of the distance that particle is from the axis of rotation. So when her arms are like this, there's very few masses with a large radius, but when they're like that, then she's got more masses with a large radius, and that mr squared for each of those gets larger and larger with her arms spread. So her moment of inertia is quite large, and the spinning is taking place on an ice surface. And if she's even touching the ice surface, it would just be like a little tip of the blades of her ice skates, so that there's very little possible torque that can be applied to her. And as you know, when the net torque acting on a system is zero, the angular momentum is conserved. That's what's required for the angular momentum to be conserved, is the net torque on the system be zero, just like the net force on a system being zero is what's required for the conservation of linear momentum. So in this case, the L that she has when her arm, the L being angular momentum, the L that she has when her arms are stuck out is exactly the same as the L that she has when her arms are together. And you can sort of look at it like this. Let me give you a little equation. So we're saying L initial is equal to L final, which means initially, remember her arms are out, so I is really, really big, and L is equal to I times omega, so her angular speed's really small. But then all of a sudden, she is going to pull her arms in, and that means the moment of inertia is going to get small, but her angular speed's going to get large. So that's really what's going on, and that's why you speed up. And you can see this, if you just go out to a playground, sit on a swing set, with the chains hanging down or whatever. If you take and twist yourself around and around and around, be careful. There's some swing sets that aren't meant to hold people our size, and could actually hurt you doing this. So be careful with that. But if you actually rotated it slowly at like a public park, you would build up enough tension in our torque from the chains wrapping around themselves that as soon as you took your feet off the ground, the chain would start to unfurl, and that would cause you to spin around and rotate. Now, if you have your arms tucked in like this and your feet tucked in up under your butt, then your moment of inertia is really small, so you'll be going really, really fast. But if you slowly or even quickly push your feet out and maybe even stick one arm out, that's going to slow you down quite a bit because your moment of inertia then went up. So your angular velocity must go down. That's the archetypal example of conservation of angular momentum. Okay. Now, the picture I was referring to was actually a round disc on which a teacher is standing, say, and the teacher is holding a wheel like this with two hands, and the wheel itself is, let's say, rotating this way, which means the angular momentum of that is upward. Okay. So I might have drawn the different direction. Nope, I drew the right direction. So that's the angular momentum. Now, what they ask you in a conceptual question is explain what happens when the instructor takes the wheel that's spinning like this and turns it upside down. Okay. The only forces that are acting there is the teacher acting on the wheel, and the teacher wheel and spinning disc that the teacher's standing on are all part of the system. So those forces are internal and therefore don't count. You don't have to have them in the summation of the torques is equal to dl dt. You don't have to have them that way. So the angular momentum must be conserved. So when the person takes the wheel and turns it upside down, the angular momentum that was just plain L, so total angular momentum initially is just plain L, but then afterwards you're going to have negative L as the moment of inertial. So total, or excuse me, as a total angular momentum. So since he turned it over or upside down, the angular momentum for that part is negative L, but you also have an angular momentum associated with the teacher. Okay? Now, in order for conservation of angular momentum to hold, that means for L to equal negative L plus LT for the teacher, we must have L for the teacher equaling 2L. Okay? Because 2L minus L gives you L again. Does that make sense? So when the instructor takes and turns the wheel upside down, the wheel, which was spinning as seen from above counterclockwise, is now spinning as seen from above clockwise. And what's going to happen is to compensate for that, conservation of angular momentum is going to force the teacher and the disc that they're standing on to rotate in the opposite direction. In other words, in the original direction that the wheel was rotating, the person and the disc have to rotate in that direction now. So the teacher is going to now be rotating counterclockwise as seen from above, while the wheel rotates clockwise as seen from above. And that is all because conservation of angular momentum. Anybody have any questions on that? All right, so that's just a nice little example, and there's some other ones in here. Your book does a really excellent job. Giancoli here does a really good job with allowing you to use angular momentum and conservation of angular momentum to analyze how you go about balancing a car tire. So that's the first time I'd seen this covered in a physics book, so I was really happy with it. So definitely check it out. Hopefully that'll work. I'll remind you that our formulas are L is equal to R cross P. And of course, P is equal to MV. And then under certain circumstances, L is equal to I omega, but not always. So I've been hinting at this L being I omega, and your book shows you a very specific example where L is not I times omega, specifically because in that case they actually have an object that's a rod that's massless going diagonally like this, and then it has a massive ball on each end, and it's rotating about this axis, this white pencil's axis. And because of that, the angular momentum for this one points that way. The angular momentum for this one points that way. There's no way you can make the angular momentum L be parallel to the omega vector that we talked about before. So that's an example where L does not equal I omega. So just keep that in mind. We also have the summation of the torques is equal to I times alpha, or the summation of the torques is equal to dl dt. And because of that, we see if the summation of the torques is equal to 0, then dl dt is equal to 0. And what does that tell us about the L vector? If dl dt is equal to 0, what do we know about the L vector? Looking to see if anybody's typing anything in the chat. It does not appear that anybody's answering. So this is a fundamental idea. This is something you should have in your brain already because I've said it like 15 times and said it, in fact, today. Momentum is conserved only when the net external force on the system is 0. That's when linear momentum is conserved. And angular momentum is conserved when the net external or when the net torque on the system is 0. And the reason why, as you can see here, is when the torque is 0, dl dt equals 0. And if dl dt equals 0, then L has to be a constant. Now it is a vector, so it's a constant vector, but the main thing is that means L initials got to equal L finals, got to equal L a little bit later, got to equal L a little bit later, got to equal L a little bit later still. Okay, so that's the key to understanding this. You also have to remember that that summation of the torque equation has very specific conditions under which it's valid. So make sure you're reading your book about that. I did highlight those key points and shared it. So I know sometimes my students can go into the copy of the textbook in mastering and they'll see my comments, but sometimes they're not there. So I don't know if they're going to be there or not. So you got to kind of read with a fine tooth comb to look for what's going on. So what they tell you again is the total angular momentum of a rotating object remains constant if the net external torque acting on it is zero. So that's one of those fundamental laws. That's one of those chucker questions that us instructors say, God, if I give this student this question, that's just like handing them this really nice gift. But then when we go and do it, we find out that a lot of students just miss it. So if you're one of those, you deserve to get that bad grade. So don't do that. All right. Don't be that student that misses that we've said 1,000 times and we think it's supposed to be extra simple. All right. Now with that in mind, let's work a problem. Let's work example 11.1, and this one's pretty straightforward. So example 11-1, and it says a small or object rotating on a string of changing length. So a small mass M is attached to the end of a string, revolves in a circle on a frictionless tabletop. The other end of the string passes through a hole in the table. Initially, the mass revolves with a speed of V1 equals 24, or excuse me, equals 2.4 meters per second and a circle of radius 0.80 meters. The string is then pulled slowly through the hole so that the radius is reduced to R2 equals 0.48. What is the speed V2 of the mass now? So let me draw a picture so that'll make a little bit more sense to you guys. So this is sort of our table. There's a little hole. This is the path that this particle is traveling around. And we, in fact, say that it's traveling with a velocity v1. That vector should be, in some sense, perpendicular to the radial line and therefore tangential to the circle. But here's our little string sticking down on the bottom here. Okay. Now, what we're going to do is pull that string so that all of a sudden the circle gets markedly smaller. And now we have a velocity v2. And this is R2, and this is R1. And what we have is R1. Notice I'm using lowercase. Your book used uppercase. That's okay. R1 is 0.80 meters. V1 is equal to 2.4 meters per second. R2 is equal to 0.48 meters, and V2 is what we want to know. Now, it is frictionless, so we at least have that. But the main thing is, because this thing's spinning around in a circle and it's frictionless, there's really no net torque added to the system. The system is the string, which is massless, the mass on the end of the string, which is not massless, but they didn't give it to us, and it doesn't matter anyways because it's going to cancel out. And that's basically the whole system, right? So when I pull the string down through the hole in the middle, that is a radial force. In other words, it's a force that acts towards the center of rotation and therefore can't be a torque. So the net torque on the system is zero. And because of that, we can say L is equal to a constant. And in this case, we do have L is equal to I times omega. And I, for a mass on the end of a string, is just mr squared. So we have I1 omega 1 is equal to I2 omega 2. We also know that V is equal to R times omega. And we also know that I is equal to M R squared. So this is going to become M R1 squared, and then omega is going to be V over R1, and then we have M R2 squared, and omega 2 is going to be V, this should be V1 up here, by the way, and omega 2 is going to be V2 over R2. you can see that the R2 cancels out that exponent there, the R1 cancels out that exponent there, and the M's cancel out automatically, so that what we get is V2. Oops, I didn't mean to write that in red. What the heck? I'll write it in red. I like it. So V2 is in fact going to be equal to R1 over R2 times V1. So V2 is equal to R1, which is 0.80 meters, over R2, which is 0.48 meters, times V1, which is 2.4 meters per second. And with this in mind, I get zero point 0.8 divided by 0.48. That gives me 1.667 times 2.4, and that gives me 4.0 meters per second is equal to V2. Any questions on that? Okay. Now we're going to do another example. This one's example uh, 11.2. And what this one says is clutch. A simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in a piece of machinery. The two plates have masses MA equals 6 kilograms and MB equals 9 kilograms with equal radii R0 equals 0.60 meters. They are initially separated. Plate MA is accelerated from rest to an angular velocity omega 1 equals 7.2 radians per second and a time of delta t equals 2.0 seconds. Calculate A, the angular momentum of MA, and B, the torque required to have accelerated MA from rest to omega 1. C, next, plate MB, initially at rest but free to rotate without friction, is placed in firm contact with freely rotating plate MA, and the two plates then both rotate at constant angular velocity omega 2, which is considerably less than omega 1. Why does this happen, and what is omega 2? So let's write down the information we're given, and then I'll draw a little picture to make sure we're all on the same page and make some sense of it. So we have MA is equal to 6.0 kilograms. MB is equal to 9.0 kilograms. Uh, the radii R0 is equal to 0.60 meters. And they're plates, they're circular discs, so the moment of inertia we know is going to be 1/2 mr squared. They're initially separated, but what we know is omega A sub 0 is 0, and omega A final is 7.2 radians per second. And delta t, which is the amount of time it took to go from omega A 0 to omega A final, is 2.0 seconds. And what they want is A, calculate the angular momentum of MA. So L sub MA is equal to question mark. Part B, they want us to calculate the torque required. And that's just the torque required to get clutch A up to the angular speed it said. And then part C is next, plate MB initially at rest but free to rotate without friction is placed in contact with the freely rotating plate MA. And what we want to know is omega 1. Or excuse me, they're calling it omega 2. Omega F final is also what they're calling omega 1, so I'll write that, but they want to know what omega 2 is. So what we're looking at here is a disk like that, and then a sorta identical in that they have the same radius disk like this. Now, in this case, this is MA, and MA is rotating with an angular frequency omega 1 equals 7.2 radians per second. So that's sort of the diagram that we're wanting to you to think about. And this up here is MB. Oops, I should write that in blue. So let's begin with part A. So what we have is they want us to know what is the angular momentum of disk A. So L sub MA is equal to I omega 1, but I is 1/2 times MA, which is 6.0 kilograms, times R, which is 0.60 meters squared. So that's just 1/2 mr squared for a cylinder. We're ignoring the little shaft up at the top, the axle part. Okay. In general, that radius is so small that it could, in principle, be a very negligible amount of angular momentum and mass. Therefore, we don't have to worry about it, our moment of inertia. But that's what we're talking about here. And omega 1 is supposed to be 7.2 radians per second, like that. So the initial angular momentum of A should be zero point 0.5 times 6 times zero point 0.6 squared times 7.2, and that gives us units of kilogram meters squared per second squared, which is the moment of or the angular momentum units. So this is 7.776 kilograms meters squared per second. And that's really only good to 2 sig figs, so I'm going to underline those other digits, and we'll say this is the answer to part A. And that's pretty straightforward. Anybody have any questions on that part? All right, for part B, what they want to know is what torque could actually cause that. So torque is equal to I times alpha. So we need alpha, and I is going to stay the same. That's 1/2 mr squared, but the alpha is going to be omega 1 minus omega 0 over delta t. So we're going to have 1/2. I'm going to leave off the units this time because obviously the units just make it a little messier and hard to fit in here. So 1/2 mr squared is going to be 1/2 times 6.0 times 0.60 squared. So that's the I. And then omega is going to be 7.2 minus 0 over 2.0. And that's going to give us basically kilogram meter squared per second times radians per second per second. So that should actually give us Newton meters as the unit. Let's go ahead and multiply it though. So I'm going to say zero point 0.5 times 6 times zero point 0.6, that one's going to be squared, times 7.2, and now I'm going to divide that by 2, and that gives me 3.88. So torque is equal to 3.888 Newton meters. Again, there's only 2 sig figs there, so I had to underline those other digits. But that should be roughly 3.9, which is the same units or the same amount your book got. Now for part C, what they want to do is they want to know omega 2. So I'm going to use conservation of angular momentum to do this. And conservation of angular momentum says that 1 half ma r0 squared times omega 1 is equal to 1 half. Now, this is going to act like it's a bigger cylinder, but the same radius. So it's going to be 1 half ma plus mb times r0 squared times omega 2. Notice the r zeros squared are going to cancel out. The 1 halves are going to cancel out. And all we ultimately have is that omega 2 is going to be MA. Actually, that's capital A that we were using. So it's going to be M sub A divided by M sub A plus M sub B times omega 1. So I can do this math. I'm not going to, just because I don't have the space here, I'm just going to work it out. The MA is supposed to be 6 kilograms, so I'm going to say 6 times 7.2. That's the MA times omega 1. Now I'm going to divide that by MA plus MB, so I'm going to say divide by parentheses 6 plus 9. Now, when I did the 6 times 7.2, I got 43.2. And now I'm going to take that 43.2 and divide it by 15 because 6 plus 9 is 15. And that gives me 2.88 radians per second. But again, that's only good to 2 sig figs. So it should be roughly 2.9 radians per second. Anybody have any questions on that? So this is the majority of the types of problems that you should expect for Chapter 11, even though you obviously should be able to compute a cross product either with the matrix method or that other matrix method I showed you, or by doing term by term. Hopefully, one of those three methods really hits home with you, and you can do it. So definitely, definitely, definitely expect on the final exam to be able to compute a cross product as well as a dot product, as well as use a dot product or a cross product to figure out the angle between two vectors. That's another thing you could do. I've hinted at that, and I actually showed you how to do that with the dot product. So, but you can do it the same way with the cross product as well. So, anyone have any questions? All right. So, example 11, 3 is an estimate one, and I like it a lot because it's related to related to astronomy. So, let's do this. Example 11-3, and it's called neutron star. It says astronomers detect stars that are rotating extremely rapidly, known as neutron stars. In fact, one of the first ones that were ever discovered, they actually labeled it as LGM for little green men because basically a source of light was hitting us, and it was hitting us very rapidly, so rapidly that we were convinced nothing natural could cause it. It was like on the order of hundreds of times per second or something like that. And it was really consistent, like it was good to a couple decimal places, and that's again indicative of some kind of intelligence possibly. So they wrote LGM question mark by it when they saw it, and later what they discovered, it was actually just a neutron star, and that's how we discovered neutron stars existed. Even though we had some idea that neutron stars, black holes, white dwarfs, and those sort of things could actually be possibilities that would come up from the normal life cycle of a star. So, anyways, it says astronomers detect stars that are rotating extremely rapidly, known as neutron stars. A neutron star is believed to form from the inner core of a massive star that collapsed under its own gravitation to a star of very small radius and very high density. Before collapse, suppose the uh, suppose the core of such a massive star is the size of our sun, which is R is approximately 7 times 10 to the fifth kilometers, with a mass of 2.0 times as great as the sun, and is rotating at a frequency of about one revolution every 100 days. If it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, what would its rotation frequency be? Assume the star is a uniform sphere at all times and loses no mass. So we're going to say R1 is 7 times 10 to the fifth kilometers. We're going to say M1 equals M2 equals 2 times the mass of our sun. That's the symbol we use for our sun. Circle with a dot in the middle. Not that we necessarily need it, but anyways, the angular frequency initially is equal to one revolution per 100 days. And what we want to know is omega 2. And what we know is R2 is going to be about 10 kilometers. Okay. So what we have here is conservation of angular momentum because obviously you probably can't even think of something that could apply a torque to a spinning star, right? And if the net torque acting on a system is zero, then dLdt is zero, and dLdt being zero means L is a constant. And if L is a constant, that means L is conserved. So we're going to do that. We're going to say L1 equals L2. And in this case, because of the high symmetry, we can use L equals I omega. So the I is going to be 2/5 M1 times R1 squared times omega 1 is equal to 2/5 M2, but remember M1 is equal to M2 because he told us to assume no mass was lost. But R2 is definitely different. So the I omega, or the I is 2/5 MR2 squared. And then we have omega 2. So the M2 is going to cancel out with the M1. The 2/5 is going to cancel out with the 2/5. And really what we get is omega 2 has got to equal R1 over R2 quantity squared times omega 1. When I do that, that means I'm going to have 7 times 10 to the fifth over just plain 10. Notice I'm using kilometers in both cases. That's why it's acceptable to use kilometers because you can see that they are clearly canceling each other out. And this is basically 7 times 10 to the fifth divided by 10 is 7 times 10 to the fourth. So that's going to be 49 times 10 to the eighth. That's a huge number. And then omega 1 is 100 revolutions, or excuse me, one revolution per 100 days. I'm going to say that a little differently. One revolution per 100 days is I'm going to convert this to revolutions per second. So I'm going to say 1 day is equal to 24 hours. And then I'm going to say 1 hour is equal to 3,600 seconds, like that. So let's do that one real quick just to see what one revolution per 100 days is. So I'm going to say 1 divided by parentheses 100 times 24 times 3,600. All of those were in the bottom, close parentheses, and this gives me 0.000001157 revolutions per second. So way, 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 way smaller than a single revolution per second. Now I'm going to take that number and I'm going to multiply it by parenthesis 7 times 10 to the fifth divided by 10 close parenthesis, and now I'm going to square that 7 times 10 to the fifth divided by 10, and that's going to give me 567.1 revolutions per second. And in fact, we're really only dealing with one sig fig, so I have to underline all that. So we're going to say omega 2 is on the order of 6 times 10 to the 2 revolutions per second. Now, just to give you an idea how big that is, uh, that's on the order of 600 hertz, which is about 3,600 RPMs. Excuse me, 36,000 revolutions per minute. Any questions on that? All right. Here's another neat little conservation of angular momentum sort of problem. Let's do, this is example 11-4. And it says running on a circular platform. Suppose a 60 kilogram person stands at the edge of a 6 meter diameter circular platform. So M is 60 kilograms, and the diameter is 6.0 meters. It says, suppose a 6 kilogram person stands at the edge of a 6 meter diameter circular platform, which is mounted on frictionless bearings and has a moment of inertia I equals 1,800 kilograms meters squared. The platform is at rest initially, but when the person begins running at a speed of 4.2 meters per second with respect to the edge of, or excuse me, with respect to the earth around its edge, the platform begins to rotate in the opposite direction as in figure 11.5. Calculate the angular velocity of the platform. So now that I have that, I also have to write down this other information I have, speed. So V2 is equal to 4.2 meters per second. Now, they told us this disk was on frictionless bearings and that sort of thing. That's code word for, hey, there's no torque on this system. Basically, the person applies a torque on the disk, and the disk, in principle, could apply a force onto the person, but the disk and the person are part of the system, so they're internal forces, and we don't count them. Therefore, the net torque is zero, and when the net torque is zero, that means the derivative of the angular momentum with respect to time is zero, and that means the angular momentum is a constant, and that's the definition of conservation of angular momentum. So what we're going to do is we're going to say L initial is equal to zero, but then L final is equal to, we have the person at the end, so that's going to be M times d over 2 squared. That's the moment of inertia for a point object, which is what we're assuming the person is, a distance d over 2 away from the center of rotation. It's just mr squared, right? So that's our I. Our omega, however, is something a little different because what we're asked to find here is calculate omega. So we're wanting to find omega equals question mark. What we do have is this person running with an angular velocity from v equals r omega. We know that omega for the person would be equal to v over r. So we could say v2 over d over 2. Now that's the angular momentum of the person. Now, the angular momentum of the disk is I for the disk times omega squared. So that's really what we're, excuse me, times omega, not omega squared. That's the expression we're looking for. Now we can say L initial equals L final. That means 0 is equal to m d squared over 4, because that's what happens when you have d over 2 squared. And this is 2v2 over d plus I omega. So we can figure out that omega must be equal to negative md. Notice what I've done is this d down here cancels out with that d down there, and this 2 up here cancels out, leaving a 2 down here. So I'm going to say md v2 over 2. And then, of course, I got to divide by I, so I'll put the I down here. And the negative is just going to indicate that, hey, we're saying the person's running, let's say, counterclockwise. The disk is going to therefore rotate clockwise. So in this case, I'm going to say negative 60 kilograms times 6.0 meters times 4.2 meters per second divided by 2 times 1800 kilograms meters squared. Like that. That should give it to us. And it looks to me like we're going to have kilograms meters squared per second divided by kilogram meter squared. So that just means per second. And of course, we can throw in a radian anytime we want. So we're going to call that radians per second. So I'm going to take 60 times 6 times 4.2, and I'm going to divide it by parentheses 2 times 1800, close parentheses, and that's going to give me omega equals negative 0.42 radians per second. Now, radians per second, we could convert that to another unit if we wanted, but this is good enough, so we'll leave it at that. Anybody have any questions? I will tell you that something we need to know about angular motion. Remember, omega is equal to 2 pi times the frequency, and frequency is 1 over the period. So once you have omega, you can, in principle, go ahead and calculate the frequency. In this case, that would be how often a dot on the circular disk approaches you every second. So, for instance, if you're watching the disk go around like this, each time a dot gets next to you, you start timing, and boom, you time it, boom, you time it, you keep on timing it like that. What the F is the number of times that dot passes you in a single second. The period, on the other hand, is the time between that dot getting to you and coming back to you. So those are some quantities that come in handy, and we'll definitely see more of that in chapter 14. But anybody have any questions on this? Example 11.5 is basically the one I just worked for you at the very beginning of chapter 11, where we worked with a teacher holding a wheel spinning like that. So that one's taken care of. There is a nice example, though, that I want to show you. They go here at section 11.2, they go into the vector cross product. I've already talked to you about that. I've shown you how to do it a couple different ways, 3 different ways specifically. So hopefully you're good to go on that. We're going to carry on. And I'll just, in terms of that, just so we're all on the same page, in case somebody might have some confusion as to why that's helpful. What we learned was torque is equal to R cross F. So that's one reason that you'd want to know what torque is. But also, angular momentum is R cross P, and of course P is equal to mv. So the L equals R cross P and the torque equals R cross F is reason enough for us to want to know how to do cross products. Just for the record, let me show you another way. Let's say R is equal to this vector. I'm going to say 1, 2, 3. That means the x component is 1 meter, the y component is 2 meters, and the z component is 3 meters. And let's say F, again, I'm writing it in this shortened notation. F is going to be 4, comma 5, comma 6, and that's in newtons. So the x component is 4 newtons, the y component is 5 newtons, and this z component is 6 newtons. So torque, which is R cross F, I could write out that determinant, but what I want to do is show you another quick and dirty way. 1, 2, 3. Actually, I don't want to write it that way. I want to put it here as 1 I hat plus 2 j hat. I'm going to ignore the units and throw them back in later. 3 k hat. That's going to be crossed with 4 I hat plus 5 j hat plus 6 k hat, like that. Now, this gives me 1 times 4 times I hat cross I hat. And I hat cross I hat, since A cross B in magnitude is the magnitude of A times the magnitude of B times the sine of the angle between them when they're tail to tail, this gives me 1 times 1 times the sine of 0 degrees, which is 0. That's for this term. Now I've got to do this term, which is plus 1 times 5 times I hat cross j hat. And I hat cross j hat is positive k hat. Technically, that was a zero vector that got, by the way. Now I've got to do the first term with the third term. That's going to be plus 1 times 6 times I hat cross k hat. Now, I hat cross k hat is not a cyclic permutation. That's one way of thinking about it. But you can also use a right-hand rule. And if I go I hat cross k hat, that gives me the negative I hat, or excuse me, negative j hat. So just using a right-hand rule and using a right-handed coordinate system, there's x, there's y, there's z. That means that's k hat. This is j hat. And this is I hat. So if you do I hat cross k hat, you can see I hat cross k hat points to the left. That's the negative y direction. Therefore, it's negative j hat. Now I can do the second terms like this. So I'm going to say plus 2 times 4 times j hat cross I hat. Now j hat cross I hat is negative k hat. Again, check that with your right hand rule on the drawing to the right there. Plus 2 times 5 times j hat cross j hat. Now j hat cross j hat is 0. And then we say plus 2 times 6 times j hat cross k hat. J hat cross k hat is actually I hat. So that works out. Remember, there's always going to be a magnitude of one because the magnitude of I, the magnitude of j, and the magnitude of k are all one. So one times one is always going to give you one. Then it's just a matter of the sine of the angle between them. And if they're different, then the angle is clearly 90 degrees, but it could be 90 such that the sine gives you a negative, or it could be 90 such that the sine gives you a positive, or more specifically, the right hand rule is what's dictating the positive or negative. Now I'm going to also finally do the third term. So this will be 3 times 4 times k hat cross I hat. Now k hat cross I hat is j hat. And then I'm going to do 3 times 5 times k hat cross j hat. And k hat cross j hat gives me negative I hat. And then finally, we're going to have 3 times 6, but it's k hat cross k hat, which is 0. So ultimately, what we have is 5k hat plus, or excuse me, minus 6j hat, minus 8k hat plus 12 I hat plus 12j hat minus 15 I hat. Now I can combine like terms. I'm going to say 12 minus 15 is negative 3 Newton meters I hat, plus that takes care of the 12 and the 15. The J is negative 6 plus 12, so that's going to be 6 Newton meters J hat. That takes care of that one and that one. And then 5 minus 8 would be plus negative 3 Newton meters K hat. So that is what the torque is, and that's yet another example of how to actually calculate that. I'm actually feeling okay with how far I got in chapter 11 because I really just wanted to make sure I got through the problems that I've done there. So that's not too terrible. I think we're in a good spot there. Example, I'll leave conceptual example 11.7 up to you. I just want to remind you that when you're doing a point particle, then R cross P makes perfect sense. It's just R times M times V if the velocity is literally perpendicular to the R. In other words, if the thing is traveling in a circle, then the R is the radius and the velocity is perpendicular to that, so that you just get times the sine of 90, and sine of 90 is 1. So you just get R times M times V. So that's conceptual example 11.7. So I'll just say, and we'll move on from there. See if there's anything else that jumps out at me that I feel like I really need to make sure I cover. Page 111 or 311, that's where they told you about when the equation summation of the torques is equal to dl dt about the center of mass. So make sure you read that. It specifically says equation 11.9a is valid when L and T external are calculated with reference to a point fixed in an inertial reference frame. It is also valid when T external and L are calculated about a point which is moving uniformly in an inertial reference frame, since such a point can be considered the origin of a second inertial reference frame. It is not valid in general when T external and L are calculated about a point that is accelerating, except for one very special and important case. when that point is the center of mass of the system. So if you're doing if you're doing the rotation about the center of mass of the system, then the equation is valid. So make sure you know that just so you can apply it. I'm not going to nitpick and try to ask you little pointed details about that. I just want to make sure you know when it's valid because it's going to come in handy if you take dynamics, which most people have to. They take statics and they take dynamics. Section 11.5, the one thing I want to do is the Atwood machine, and we only got a couple minutes left, so this will be a good one to do. So, example 11-8 is an Atwood machine. It says an Atwood machine consists of two masses, MA and MB, which are connected to an inelastic cord of negligible mass that passes over a pulley. If the pulley has a radius r0 and a moment of inertia I about its axle, determine the acceleration of masses MA and MB and compare to the situation the moment of inertia of the pulley is ignored. Ignore friction. So here's our diagram. This is a pulley of radius r0, and it also has a moment of inertia I. What we're going to do is imagine hanging from this is a mass m1, and hanging from the other side is a mass m2. And what we want to calculate is specifically the acceleration. The tension is something that would be worthwhile as well. So I'll probably at least point at that. So first off, I'm going to take the summation forces in the y direction equals mass times acceleration in the y direction for m1. So what it looks like from this diagram, it looks like M1 is going to be going down and M2 is going to be going up. I'm trying to make a coordinate system that'll be consistent with that for all three of my free body diagrams. So what I'm going to do is I'm going to draw this downward as if it's the positive y-axis points downward. I have a mass M1 here. Acting on that mass M1 is a force M1G, but also acting on that mass is a tension that I'm going to call T left. Now it's T left because imagine this: if if the T that I've just drawn is rotating, is pulling on that pulley, then it has to supply enough force to rotate the pulley and to lift up the mass M2. However, if I considered it just at the right hand side of the pulley, the tension would only need to be the tension required to lift M2. So that's why there's a reason for us calling TL and TR as if they're different. So in this case, the summation of forces in the y direction gives me M1, oops, let's write in blue again, gives me M1G minus T left is equal to M1A. Now, I'm not subscripting the A because we're assuming the string doesn't get loose, doesn't get any slack in it, and the string doesn't stretch. So if it moves up an inch, the other one moves down an inch. If it moves up an inch in a second, the other one moves down an inch in a second. So even the velocities are equal. If the accelerations on one side is, it goes from 1 inch per second to 2 inches per second in 1 second, then the same thing's going to happen on the right. So I'll just call it A. That's going to be equation 1. Now I'm going to do the right hand side, and in this case up is the positive direction. That's got to be consistent. That makes it consistent where the acceleration of M1 is positive when the acceleration of M2 is positive. So in this case, I'm going to have a mass M2, and I have acting on it a tension T right, but I also have acting on it this time in the negative direction a weight M2G. So this gives us T right minus M2G is equal to M2A, and that's going to be equation 2. Now I've got to do a free body diagram for the pulley. And to do that, what I'm going to realize is that the uh, pulley rotating counterclockwise is consistent with the M1 going down and the M2 going up. So I'm going to make counterclockwise the positive direction. And therefore, I'm going to say this is a positive tension TL that causes a positive torque TL times R0. And this one, on the other hand, is a tension T right that produces a negative. And now I can take the summation of the torques is equal to I times alpha. In this case, it's going to be TLR0 minus TR, or excuse me, yeah, TR times R0 is equal to the moment of inertia of the pulley, I, times the alpha. That's going to be equation 3. Now, since the rope doesn't get slack, doesn't stretch, and doesn't slide on the pulley, it's essentially rolling without slipping. So we know that A is equal to R0 times alpha. So that's equation 4. Uh, all we have to do to solve this is I can go ahead and substitute 4 into 3. And when I do that, that's going to give me TLR0 minus TRR0 is equal to I times A over R0. So that works pretty well. I can also rewrite that as TLR0 squared minus TRR0 squared is equal to I times A. And with this, I could, in principle, actually, let's do it another way. Let's say TL minus TR is equal to I times alpha over R0 squared, excuse me, I times A, not alpha. Okay, so TL minus TR is kind of helpful. I'm going to call this equation 5. Now I'm going to take 1. I'm going to take 2 minus 1, so equation 2 minus equation 1. That's going to give me TR minus M2G minus M1G plus TL is equal to, did I want this minus? I think I wanted those added. My fault. Let's add them. And we're about out of time. You can go ahead and go if you need to. That's okay. I understand. I'm going to go ahead and finish up this problem. I'm going to take 2 and add it to 1. So I'm going to get TR minus M2G plus M1G minus TL is equal to M1 plus M2. Notice they both had an A in it, so I just decided to factor it out. And right here, I can see that I got a TR minus TL plus M1 plus M2 times G is equal to M1 plus M2 times A. So now that I have TR minus TL, I can replace that with what I have in equation 5. So 5 implies this would be negative IA over R0 squared plus M1 plus M2 times G. Wait a second, that's supposed to be M1 minus M2. Glad I caught that now. That's M1 minus M2. So that's M1 minus M2. And all that is equal to M1 plus M2 times A, and you see that I could now have, for instance, M1 minus M2 times G is equal to M1 plus M2 plus I over R0 squared times A. So A is just equal to M1 minus M2 over M1 plus M2 plus I over R0 squared, all of that times G. And that's it. That's the what they were asking us for. You can now go back and solve that for tension L and tension right, but that's it. Text me your name if you haven't already. Let me know if you're in the asynchronous class or not. And you guys have a good day. Thanks for coming, everyone. And that looks like everybody. Let's see, anybody else here? Nope, I'm the last one. Bye, everybody. Bye.